Hello everyone, and welcome back to another video. In this video, I want to talk about index management, and we will take a deeper look at subjects such as B+Tree nodes and some code examples, asynchronous operations on B+Tree nodes, and usage of logs. And in the end, we will take a look at caching and why it will improve the performance of our B+Tree operations. As always, before we begin, I want to summarize what we have learned so far. In episode 2 of this series, we understood what is indexing and the importance of indexing in a database system. It is also mentioned that the main indexing algorithm that we will use is B+Tree. So in episode 3, we have talked about what B+Tree is. Of course, since many other YouTubers have already covered B+Tree algorithm, I have referred to their videos. But in episode 3, we have also seen the live visualization of a B+Tree. In episode 4, we understood the binary representation of a B+Tree node. And some of the code examples that we will see today is explained in more details in episode 4. In episode 5, we understood the basic idea of how index files work. We have seen how B+Tree nodes are aligned in the index file. And also we understood the problem with storing 0 in the B+Tree node. Again, understanding episode 5 topics is very important for today's video. In episode 6, we took a deeper look into index storage management, and we have covered some of the different ways of implementing index storage manager. I should also mention that in the past 6 days, I have made some changes to these implementations, and we will cover them later. But in episode 6, we have also covered topics such as file handler pool, which was very important regarding using the files in an asynchronous manner. I would also want to mention that the source of the database that I'm implementing is available on GitHub. The link of the repository is in the description. And as I have said before, I'm recording these videos as I'm implementing this database, so the code will be changing. But you can easily find these changes in my commits in the repository. To give you some few examples, as I said, after the last video, I made some changes to the index storage manager. And you can find these changes in commits from 8th of July till the 11th. But you don't need to worry about this. I will cover these changes in another video after I test and finalize them. Some of these changes are just bug fixes, and to give you an example, the close method of the class file handler would just close the file channel and set the usage count to 0, which was not the right thing to do. Now it will wait till all the threads that are working with this file finish using it, and only then it will close the file channel. Let's start by understanding this interface called Immutable Binary Object Wrapper. We have seen this interface before in episode 4, when we were looking at the binary representation of B+Tree nodes. The purpose of this interface is two things. A, to allow the B+Tree nodes to become abstract and store different type of keys and values. And B, to solve the problem of storing zeros. If we go back to the related section of episode 4, I've mentioned that to solve the problem of storing zeros, we need a class which can provide the size of the data, and by data here we mean the key or the value that the B+Tree node is storing. The class should also be able to tell us if the data is null or not if we pass byte array of size x. It should also be able to convert the byte array to the inner comparable object, and vice versa. It should also be able to convert the inner comparable object to the byte array. Now, if we assume that the generic type of E is our comparable object, then the methods of this class provide the same functionality that we need. Also, what makes it immutable is that if we have an instance of this class and we call load methods on it, these methods will not modify the byte array inside the current object, but instead they will return a new object wrapping the byte array. For example, this long immutable binary object wrapper is an implementation of the same interface, which wraps objects of type long. In order to support 0 as a value, it stores one additional byte as a flag. So the size of this object as bytes equals to the size of long as bytes plus 1. To load a long object into this class, we first create a new byte array, set the first flag byte to 1, convert the long input to byte array, and then we copy it into the rest of the output byte array. Also, to see if the wrapper object has a value, we check if the first byte, which is the flag, is empty or not. The next class is abstract tree node. Both of the different types of a node extend this class, and we have covered the methods of this class in previous videos as well. But now we can understand that the tree node depends on the immutable binary object wrapper interface of the same type as the node key in order to work properly. This abstract class mostly handles operations around the node keys. Again, as we have seen before, these methods need to know the degree of the tree and the value size. The value size always equals to the size of a pointer in an internal tree node. So in this subclass, none of the methods related to keys expect the value size to be passed. But for leaf nodes, we have a separate abstract class which requires one more immutable binary object wrapper to be used for values. And then the methods related to reading keys will use the size of the immutable binary object wrapper class passed for the generic value. Basically, all of these classes hold the byte array, which we have seen in previous videos about binary representation of B+Tree nodes. Also, all of these methods are used to modify the same byte array per each node. The main implementation of this interface is called B+Tree Index Manager. In its constructor, it requires us to pass the degree of the tree, index storage manager, which we covered in last video, IO session factory, which since it may be removed, I won't cover it in this video, but it simply acts as a bridge between index manager and index storage manager, and it allows transactional commits or lets you roll back changes if something goes wrong. Next, we need immutable binary object wrapper for both key and value generic types. And at last, a node factory, which takes a look at a byte array and returns either a leaf node or an internal node. We have covered the implementations of addIndex and getIndex methods and the algorithm for them before, but now we can go back to our blackboard to cover a few more details. Also, the algorithm for removing an index is way more complicated than adding or getting an index, and we will cover it in a separate video. So we want to see the connection between index storage manager and index manager. And first, I actually want to talk about how things doesn't work. So as we have seen before, we have a header for each index, and the header has the location of the root node. Then we had index storage manager, which could get the root location from this header and could also write or read the nodes into the disk. Next, we have the B+Tree index manager, and it will use index storage manager to read and write the nodes. One way of doing things was to initialize this B+Tree index manager by first reading the root node using index storage manager, and then use algorithms like BFS or DFS to build the tree and load all of it into memory. Afterwards, whenever we would make a change to this tree, we would have to commit all of the tree into the disk. But we will not use this approach of loading all of the tree into memory. Instead, we will load the nodes into the memory on demand. So let's say we have a tree like this, and all of the nodes in the color green are only stored on the disk in the beginning. Now let's say this node is our target, which stores the key that we are looking for. Instead of loading all of the nodes into the RAM and then finding this target node using B+Tree algorithm, we only load the nodes on demand. So we first load the root node. We realize that the key that we are looking for is greater, so we go to the right, then load this node. Then we realize the key is smaller, we follow this one. Again, we realize it's smaller, and then we will reach our target node. The advantage of this approach is that we will have a smaller memory footprint, but the disadvantage is that we need more disk operations. Ideally, we would want to find the balance between these two. And before we do that, I want to also mention another benefit of B+Trees. How can we find all of the keys in our tree? Or how can we loop over all of the data in our database? As we have seen before, in B+Tree leaf nodes, each node has a reference to its previous and next node. In fact, if you look at the abstract leaf tree node class, you can also see these methods to set the pointer to next and previous siblings. As a result, in this area, we have a structure like a doubly linked list. Also, due to the nature of B+Tree algorithm, we know that this list is sorted as well. Therefore, for example, to get all of the data in ascending format, all we need to do is to find the root, always go left till we find the leaf node, and then keep following the next sibling node. Also this way, we can find the size of a table very quickly. I also want to cover how creating multiple indexes for a single table works, or at least the way I am thinking of implementing it. For any table, I have at least one B+Tree index, where the type of the value is a pointer, and the type of the keys is either an integer or a long. I call these indexes per each table the cluster index. You can assume that each of the keys in the leaf nodes of this tree are the primary keys of the rows in this table. To add an index on a different column, a separate B+Tree node is created, where the node keys can be any comparable type, but the values, instead of pointing to the DB file, they point to the primary keys available in the cluster index. Going back to our problem from earlier, we want to find a solution to keep the memory usage low, but also reduce the disk I/O. To do that, we will use LRU cache. LRU stands for least recently used. Basically, you can think of it as a limited combination of a map and a queue. The queue shows how items leave the cache when the limit is reached and a new item wants to be added to the cache. But whenever we read an item from the cache, we move it to the end of the queue. This way, we prevent the cache objects that are recently used to be removed when the limit is reached. If you want to understand how LRU cache is implemented, I suggest you to head on to Frontend Master's website, search for the last algorithm course you will need, and you can use this course to understand fundamental data structures and algorithms, which also includes a whole section about maps and LRU. To implement the cache in the code, I have first created an index manager decorator. Basically, this class helps us use the decorator pattern and create different types of decorators for index manager. One of these decorators is the cached index manager decorator, and to construct it, we use Google's Guava cache builder, and we can set the maximum size of the LRU cache. The keys for our cache is a table identifier, which is a record that includes the table ID and the key or the identifier that is added to the tree. So this identifier equals to the keys in our tree. Then, after we add a key and value to the tree, we also add it to the cache. To get a value corresponding to a key, you first look it up in a cache. If it's available, we use the cached value. If it is not, we will request it from the decorated class and then add it to the cache. Also, if we remove a key, we will invalidate the value from the cache as well. I've also created a different cache using maps, which per each table or index keeps track of the size of that index. And I increase or decrease this value as I add and remove indexes. In previous video, I have talked about the different implementations of File Index Manager. Also, we understood that depending on our use case, we may need a database level lock or just index level locks. Now, if we come back to the code, this Index Manager decorator has two more implementations. One of them is DB level async index manager decorator. The other one is table level async index manager decorator. If we look at the DB one, for example, the idea is that when a thread is writing to an index, no other thread should be able to read. Also, when threads are reading from an index, no other threads should be able to write. In Java, we can use reentrant read-write lock to achieve this behavior. So in the DB level lock, we lock the write lock when we are adding an index or removing an index. We lock the read lock only when we are getting an index. This whole concept is also known as reader-writer lock, and you can read more about it in this Wikipedia page. At last, for the table level lock, we use a map as a lock pool, and for each table, we create a separate lock. So if we look at the lock manager, it again has reentrant read-write lock, which is used in the methods of this decorator. Thank you for watching this video. If you have any questions regarding the contents of this video, feel free to ask them in the comments section. If you enjoy these videos, make sure to press like and subscribe to the channel. Also, to support my work, you can use the information in the description. See you in next one. Take care.